All right, so today I'd like to continue on with review. We are going to be jumping into Unit 2. I'm hoping we can get through all of Unit 2 and maybe start Unit 3. We'll see how that goes. Again, if you want to use this hour to study, to do whatever you need to do to get ready for that test on Friday, you do what you do. If you want to follow along with me, awesome. That's perfectly fine. Grab that gigantic review packet and yeah, we'll get started. Number 1 is tied to number 2. In number 2, they give you this chart of electronegativity. Okay, so in order to answer like which of these bonds is the most polar or most non-polar, a chart of electronegativity is going to help. I was ready for you. All right, so feel free to get started, okay? I will eventually run through a good chunk of these. Again, I'm going to be picking and choosing which ones are the most relevant. So if I skip a problem and you're like, wait, I wanted to do that one, you totally can. The answer key's posted. Just, you know, you do you. But for this first one, please use the table from number 2. The only way you're going to answer this stuff is by using the electronegativity table given to you in problem number 2.
Oh yeah, have you decided on if you're going to do a final for those 14 tests?
Yeah, I probably will. Okay. It won't be too extensive, but yeah, I will.
So like this is the second semester then, or will it be everything that we've learned?
It'll be a smidge of everything, if I'm being honest with you. But again, don't anticipate it being, you know, I'm not giving you a 3-hour. I'm not giving you a 3-hour 15 by any means.
Yeah.
Pro.
You should grow out a pro.
Yeah, definitely. No, I have. It's called. I have a sty. So I have a blocky duck under my eyelid.
They get like.
Yeah, it's really fun. Yeah. No, I don't like that.
You see that? Kids are.
Yeah. So my eye's been swelling up for the last couple days. It's healing. I can feel it's a little better, but yeah, it's been biting me.
Just unblock.
I'm working on that. I went to the doctor and they gave me some eye stuff, and we'll be good to go. What's that? Maybe.
Are they gonna ask me to classify bonds on the test?
Potentially, yeah.
Okay, so like the first one.
Yes, I think so. Never mind. Second one. Now, let me point something out really, really quickly. I know you're kind of working on this, or you should be working on this. With this question, the way it's worded, let's talk about that for just a second. If you remember, chemical bonds or bonding is on a spectrum, okay? So what I mean by when I say that is, it's not black and white. It's not covalent, ionic. There's more to the story, okay? We classify bonding based off of how equally the electrons in that bond are shared. If the electrons are shared perfectly evenly, we call that a nonpolar covalent bond. Now, how can we determine that? We can determine that by looking at electronegativity. What's electronegativity? It's related to, it's related to electrons. It's a word I taught you in September. That's the definition.
Yeah, that's how it works.
Electronegativity describes how strongly an atom will attract bonding or shared electrons towards its nucleus.
Wait, what was the word?
What? Electronegativity.
Oh. I thought there was one word that was. Like,
Oh, no, I'm sorry. I was
It was
making a
so
joke.
confusing.
I was making a joke. I'm sorry. So electronegativity is how strongly atoms pull shared electrons towards their nucleus, okay? So a bigger value of electronegativity means that that atom has a stronger attractive force or a stronger pull on the shared electrons in a chemical bond. So for example, if we look at this first one, I have phosphorus and I have nitrogen. So if I find phosphorus, the electronegativity is 2.1. If I find nitrogen, electronegativity is 3.0. The difference between them will give you an indication of how polar or how unevenly shared that bond actually is. So this has a difference of 0.9. Okay. The next one, H and P. Did you look those up? What's the difference? Nothing. CN, SRS, 1.5. You said 2.1, 2.8. Holy crap! Big difference. Okay. Now, the bigger the difference, the more unevenly the electrons are shared. The smaller the difference, the more evenly the electrons are shared when these two elements make a bond. So there's kind of this cutoff. If it's really, really low, or 0, we call that nonpolar covalent. What that means is there's not a partial charge on either side, and the electrons are shared perfectly evenly. If there's a slight difference, but it's kind of, you know, less than, usually the cutoff is like 1.9-ish, 2.0-ish. It's kind of, again, vague, and it's kind of gray in terms of how we define it. But if there is a difference, we call this polar covalent. What that means is the electrons are still shared, they're just shared unequally. So for this one, for example, the nitrogen is more electronegative, yes? As a result, the bond, which contains 2 electrons, will be pulled in the direction of nitrogen ever so slightly. And as a result, it gets a partial negative charge. And where the electrons are pulled away from, in this case the carbon, gets a partial positive charge. Ring a bell just a little bit, I hope? Okay. Now, if I want to arrange these according to their ionic character, what's an ionic bond? Metal, nonmetal. In terms of the electrons, what's happening with an ionic bond? A full transfer, meaning the electronegativity is so big that these aren't even shared anymore. One atom has basically just taken them. Okay, it's a full transfer of electrons. So when I'm describing ranking these bonds in terms of their ionic character, what I'm really trying to say is, okay, rank these according to how unevenly shared the electrons are. The more unevenly shared they are, the more ionic that bond is. So in that instance, we would call this the least ionic, or in other words, this is a nonpolar covalent, right? So this would be least, I'm going for the least to most, I guess, right? That'd be next, next, a little bit worse, and this is just about as big of a difference as you can possibly have, okay? So francium oxide, or francium and oxygen making a bond, would 100% be an ionic bond, okay? The difference in electronegativity is so huge that the oxygen would effectively take these shared electrons, or what would have been shared electrons, and fully transfer them to itself, okay? So again, it's a spectrum, and we can make predictions on that spectrum based off of electronegativity. By the way, what are the 5 most electronegative elements on the periodic table? FONCLVR, phone Chloe, bro. Those 5 hog the electrons. They take those shared electrons and pull them towards their nuclei very, very strongly. I think I might have all of them in here. F, 4.0, O, 3.5, N, 3.0, no chlorine or no bromine, but either way, those are the 5 most. Okay, I think chlorine and bromine are both right at 3.0. I think bromine's like 2.8, but chlorine I think is almost the exact same as nitrogen. Either way, okay. Correct. Fluorine is the most electronegative element on the periodic table. So with that in mind, we could do that same exercise in number 2 right here, right? I could look up this, I could look up that, I could look up this, I could look up that. And then I can classify the type of bond it is. If it's a big difference, we call it ionic. Usually, again, that difference needs to be like 1.9, 2.0, and up, give or take. All right? And if it's less than that, we call it polar covalent, meaning the electrons are still shared, they're just shared unequally. And if it's basically no different, we call that nonpolar covalent. Now, the hard part with nonpolar covalent is that there's kind of a range for that as well. Because if there's a difference of like, 0.1, 0.2, in reality, it's such a small difference that the partial charges that in theory exist are effectively worthless. So we could still call something that is a 0.1 difference or a 0.2 difference nonpolar covalent without much trouble. Again, it's a spectrum, right? There's not hard cutoffs between these classifications. Okay, so I'm not going to do this one. You're welcome to if you'd like to. Again, my cutoff I think I gave you guys back in the day was nonpolar covalent is 0, 0.1-ish, 0.2-ish if you're feeling whatever. Polar covalent runs from 0.3 all the way up to like 1.8, and then ionic runs from 1.9 and up, give or take. Okay, and again, those are not hard cutoffs. Those are very much gray, blurred lines between these classifications. Coulomb's law, yes, picking it up from yesterday. Okay. Compare the following ionic compounds. Which of these would have a greater lattice energy? What the heck is lattice energy? Do you remember what lattice energy is? Or like, I mean, can you describe it, I guess, maybe? It's literally like the attractive force between ions. Okay, now, when ionic compounds form solids, they form crystals. And we call that a crystal lattice structure. So lattice energy can be described as either the quantity of energy released when that crystal forms, or it can be described as the quantity of energy required to break that crystal structure. Okay, either of those definitions is perfectly fine. But long story short, if you have stronger attractive forces between ions, your lattice energy is greater. If you have weaker attractive forces between ions, your lattice energy is less. They will use the term lattice energy probably somewhere on that test Friday. Please don't let that freak you out. Okay? Greater lattice energy means stronger attractive force between those two ions. So we've got choices here. Let's use Coulomb's law. Let's think about this. Go for it. I'd like you to think, and then I'll fill in the gaps in a little bit. And again, don't wait for me. Keep on going. If you're content, if you're good with Unit 2, if you look over all these and it's like, yeah, okay, I kind of remember this, then you're okay.
I know, I see that.
They have more photons.
No, small. No, man, sodium is smaller. This is what I'm saying.
Yeah. Potassium has.
I need this bigger, better, farther away.
Raw Lewis Steiner. Oh, that's better one.
Yeah, well,
Those are still decent.
Okay, which of these would have the greater lattice energy? What are the two parts of Coulomb's law? Magnitude of charge and distance, aka really we're looking at size, right? Smaller particles get closer together. So in this instance, what's the charge of a potassium? Chloride? Sodium? Chloride. Okay, so the first part of Coulomb's law is not going to help us, is it? If the magnitude was different, let's say instead of this being KCl, it was CaCl2, calcium chloride. Well then, spoiler alert, bigger charges, stronger forces, greater lattice energy. But that's not what we have here. What we have here is 1 + 1 - versus 1 + 1 -. Okay, so we need the second part of Coulomb's law. The second part of Coulomb's law is distance. Smaller particles get closer together. Chloride's the same. So what's the difference between sodium and potassium? Which of those is a smaller particle? Sodium is. If you find those two on the periodic table, it's element 11 and element 19. Sodium's further up on that column, potassium's further down on that column. Further down you go, the bigger the atoms get. So sodium, being the smaller of the two cations, means that the lattice energy or the attractive force of sodium chloride would be greater than the lattice energy attractive force of potassium chloride. If you go look at the answer key, I think I have a massive paragraph describing that. I'm not really in the mood to write that, but I hope my verbal description right now is making sense. I'll say it again. Coulomb's law has two parts. If I want to compare the strength of an attractive force between ions or between protons and electrons, anything charged, Coulomb's law is what we use. Okay? Bigger charges, stronger attraction. So again, if I'm comparing 2 plus 2 minus with 1 plus 1 minus, the 2 plus 2 minus is going to win, hands down. There's nothing to think about. But if I have 1 plus 1 minus versus 1 plus 1 minus, like I do in this instance, I have to go to the second part of Coulomb's law, which is describing the distance between particles. Shorter distance, stronger attractive force. How do we get a shorter distance? Smaller things. Okay? Smaller particles pack in more tightly and get closer to one another and lead to a stronger attraction. And that is exactly why sodium chloride is our choice here. Questions? All right. It's time. I think I deleted too much.
What's up?
I don't have any formulas in my boxes. Oh, you do? Yeah, you want to read them off?
BF3, IF5, PCl5, SF6, SiCl2, SF4. And no, I don't know the names of those.
You kind of should. Most of them are covalent, so they're pretty easy to name. Right? Phosphorus pentachloride.
You should know this.
Kind of, you should actually. Okay, so Lewis diagrams. Been a while. Like 6 months. More than that, I suppose, actually. Holy crap. Okay, so please listen. This is a big deal. You need to know how to draw Lewis diagrams. Now, what's the first rule of drawing Lewis diagrams? We need the total electron count. What are we counting? Valence electrons. The total number of valence electrons to work with. So, how do I determine valence electrons for any element? How many valence electrons does boron have? How do you know that? Yeah, the column, right? The column number is your friend. Things in column 1 have 1 valence electron. Things in column 2 have 2 valence electrons. Things in column 16 have 6 valence electrons, right? The column number is giving you indication of how many valence electrons that atom would have. So in this instance, I've got a boron with 3. I've got 3 fluorines. How many valence electrons does each fluorine have? 7 for a grand total of 21 plus 3. I've got 24 electrons to work with. When I draw a Lewis diagram, first things first, I'm going to put my central atom in the middle, and I'm going to make one bond. I suppose it'll be a little more geographically, sorry, geometrically correct. Yep, those are words. Geometrically, let's try that. Okay, so I need one bond to each, right? How many electrons are in a bond? 2. So how many have I used? How many do I have left? 18. Now, The next rule of Lewis diagrams, and if you go back to that note sheet, it's really, really nicely written out for you. The next rule of Lewis diagrams is add them all to the outside first, and if there's still extras, you add the extras to the inside. Now, how do I know when to stop? The octet rule. Okay, I add outer electrons until I reach 8 electrons on everything. So, 18, 6, 12, 18. All of my electrons are on the structure. That's a good thing. That's a good first place to arrive at with the Lewis diagram. Get all of your electrons on the structure. And then you really want to do the formal charge, probably. The formula or the equation for formal charge is valence electrons minus dots and dashes. So if I want to solve for the formal charge of this fluorine, I take the valence electrons. How many valence electrons does fluorine have? 7. 7 minus how many dots and dashes? 1, 2, 3, 4, 5, 6, 7. Formal charge equals nothing. That's good. When formal charge is 0, that represents the most stable possible arrangement of electrons we could make.
Do you have to do that for both? Or like for the F and the B, or is it just the outside?
Everything. Yeah, I mean, really, if we want to be extra, extra sure, really everything. So if I go to boron, how many valence electrons does boron have? 3. How many dots and dashes are nearby? 3. So what's the formal charge of boron? 0. These other 2 fluorines would be the exact same math as that fluorine, right? So everything has a formal charge of 0. I think that's a great structure, and I don't think we need to do anything else. Okay? I'm going to do maybe like, I don't know, maybe another one of these. I'll do this one. I think this one's maybe the next hardest. Maybe either the 6th or the 2nd here. But if you want to see them all, please bust out a Chromebook. They're all on there. What? The way I talk?
No.
Thanks. What did I say my rapper name was like a month ago? No. No, I had a good rapper name a month ago. That is a good name. That's good. I'm keeping that. That is a solid. Okay, yeah, that's good. Is that not good? That's good. Don't steal that now. I trademarked that probably. Okay, how many total electrons do I have to work with? 42. Is that it? 35? Yeah, I think so, huh? I goes in the middle. By the way, the first element listed is almost always your central element. No unless.
Or did I just say almost?
Well, because there's always exceptions to everything, but
Okay, so then unless what?
you're not going to come across it, so it's fine.
Wait, but is it H2O?
So like if it was I2,
Yes?
if it was like I2 or something, would you just draw like the 2 I's next to each other and connect them with like a dash?
If they gave you something in that context, yes. It would be like, most likely it'd be a carbon compound. We'll talk about carbons in just a little bit. I'm going to give you guys like another little cheat sheet kind of a thing on organic molecules. Because weird things happen with organic molecules. 2, 4, 6, 8, 10 electrons are used. How many more do I have left? 32. I just start adding them around the outside. 6, 12, 18, 24, 30. I've got 2 left. Where do those go? On the central. Now, that's unique, okay? Most of the things they're going to give you, if they're going to make you draw a structure, it'll probably be either an organic molecule, we'll talk about that in a second, or it's going to be something like this, but most likely they're not going to have any electrons on the central atom. They might. I would be pretty surprised though. Okay, now, if we do formal charge, I'm just going to do it in my head. Fluorine, how many valence electrons? Minus how many dots and dashes? Each of those fluorines has a formal charge of nothing. That's good. Iodine in the middle. How many valence electrons? 7. How many dots and dashes around it? 7. What's the formal charge? 0. Everything's happy. We're good. We're done. Okay. Let's talk really briefly about what to do when they give you some weird carbon, hydrogen, oxygen molecule. If you've done enough practice tests, you've probably come across some random carbon, hydrogen, oxygen molecules. Okay. I would like you to write this down somewhere. I don't know if this sheet is the best place because it's probably going to get lost in all of your stuff. But somewhere you probably want to write this down. Okay. In Lewis diagrams, carbon will have 4 bonds, no lone pairs. Hydrogen will have 1 bond and no lone pairs. And oxygen will have 2 bonds, 2 lone pairs. Okay, this is gonna be true. If they give you something weird, organic, carbon, hydrogen, oxygen, whatever the heck they're trying to make you draw or fill in, follow these rules, and you should be good to go. Okay, carbon is going to make 4 bonds. Hydrogen is going to make 1 bond. Oxygen is going to make 2 bonds. I want to use the word always, but that's a dangerous word to use. Okay, 99% of the time, this is true.
So can we practice that?
Sure, let me think of something. Sure, how about this? Why don't you try, draw me the Lewis diagram of C2H4. Put this to the test. Put your knowledge to the test. Draw the structure of C2H4.
Oh yeah, you can do that. I do this, right?
Yeah. As long as you're following those rules, right?
Yeah.
There's no other possible way to arrange it.
I forgot about that.
Yeah, there's no other possible way to arrange this. There's one possibility if you're following the rules I just gave you.
Thank you. You should do it with the code.
Yeah, you should.
C2.
Let me give you a generic backbone. See how do I want to do this?
Take a look at
Wait, what's this?
this is the one who's going with the O's.
Oh, I was like, that's not C2H4.
Okay, let's see. How do I want to do this? I'm just spitballing. All right, I'm missing some hydrogens. Okay. I'm missing some hydrogens. How do I want to fill in this structure? I'm missing bonds and I'm missing hydrogens. Sorry, no. Let me do this. I'm sorry. Let me give you more. There, let's go like that. I'm missing hydrogens and I'm missing something over there too. Follow the rules. What should I do here? I'm missing 2 hydrogens, right? What about here? What about here? How many bonds am I going to have here? Why? Carbon needs 4. How many does oxygen need? 2. If there's nothing else with the oxygen, right? I've got to have 2. I could, but I didn't. I did that differently. I tried to do it differently anyway. Okay. Lone pairs. Are there any lone pairs on this molecule?
Yeah.
Follow those rules. It always works.
So is that
Yeah, I don't know what that is. Well, actually, it'd be like, yeah, what would that be called?
Is that actually?
That's the formula. That's not the name.
Yeah, when
I guess we'd call it. Yeah, it's double suffix.
Tricarbon hydrogen.
I don't know which one would take precedent. I forget. No.
Are you not gonna name the shape of them and the angles?
I guess it would be like 3-one propanoic acid.
yeah.
I don't know, but that's weird. I don't know how those double suffix would work. But anyway, that doesn't matter. Long story short, when you're doing weird carbon, hydrogen, oxygen molecules, follow these rules. Carbon, 4 bonds. Hydrogen, 1 bond. Oxygen, 2 bonds, 2 lone pairs. If any of these rules are ever broken in any of the molecules that they're showing you, it's probably not the correct choice if it's a multiple choice situation. Okay? There's one question, I have no clue which year it was, but there was one question that was trying to like show you the correct structure of a chemical reaction. And one of these rules is broken in all 3 of the options, except for the 4th option. So by process of elimination, we could have figured out which one was which. Okay? Follow these rules with organic molecules, please. It'll help. Well, no, the hard part is if you just punch in the formula, there's a lot of isomers of that formula, meaning like the specific structure of C3H6O2, there's a lot of different ways that I can arrange those atoms. So there's not going to be one true name for that molecule unless you actually draw out the correct structure. Sorry. Yes, Logan?
Are we gonna be doing the bonding or
Yeah.
whatever shapes of them?
Yep.
Yeah.
Would you like to?
No.
This one is just asking for different examples. If it's an ionic compound, metal, non-metal is still going to work for what you need, okay? If it's covalent, 2 nonmetals is still going to work for what you need. And if it's both, you need a polyatomic ion. A polyatomic ion contains covalent bonds within it, but it is charged and would form an ionic bond with whatever else is with it, okay? So I'm going to skip that. Partial charges, we can totally do this. I didn't give you electronegativity here, but which of these 2 is more electronegative? Why? That would work. It's one of the 5, right? Phone Chloe, bro. That's bro. This is more electronegative than carbon. What partial charge would go here? Whatever one is more electronegative is going to pull the electrons towards it. It's a lowercase delta in the Greek alphabet.
Wait, wasn't delta a triangle?
Yeah, that's capital delta.
You have a lowercase delta?
But did you write MC? MC write out capital and then put that.
So what does delta mean in this?
Partial charge. So this is representing like not a full 1+, but less than 1+, right? So like 0.5, 0.3, somewhere in there. There's a positive charge here. It's just not a full quantity.
So then capital delta is like complete.
No, capital delta is going to be used for like change in temperature, right? Delta T, or change in Gibbs free energy or enthalpy or entropy.
Partial change. So then that's.
This is partial charge. It's different. They're used in completely different contexts. Even though they're the same letter. That's what it is.
I hate this. It's when you have to show all the different ways of how you can. Oh, this is it's so funny. It's just annoying. Wow.
Now, in Nitrate, which is what this is, I'm going to do this pretty quickly. Hang with me. I'm going to do a Lewis diagram. How many total electrons do I have to work with? How many valence electrons does nitrogen have? 5. How many does oxygen have? 6. 6 times 3 is 18. Plus 5 gets me to 23. What's the -1 charge be? An extra. So I've got 24 to work with. I've used 6. And I am now going to be at 18 left. And I can add those to the outside. I will do so. Okay. Formal charge is not great.
Doesn't O need to have 2 bonds?
Yeah.
Oh, okay.
So if I try to fix this, what I can do is make a double bond. But here's the problem. Nitrogen cannot go beyond 8 electrons. It's in the second row of the periodic table, if you remember that nonsense. So this is as far as I can go, which means that this has a formal charge of -1. This has a formal charge of -1. This has a formal charge of +1. Because overall, this has a -1 charge, right? Now, this is where resonance comes in. They very, very, very rarely ask a question about resonance, so I'm going to be done with this in like 30 seconds. Okay? Why would resonance occur? Resonance occurs because there's equivalent structures. Here's what I mean. Does that double bond have to be here? No. Why? How is that any different than this spot or that spot? It's not. So then all 3 exist at the same time. And that's what resonance is, okay? Resonance is equivalent structures showing different locations of electrons.
So you said that, whatever, O has to have 2 bonds and 2 lone pairs. So what would happen in nitrate? What?
O has to have 2 bonds and 2 lone pairs. So that's what it really, really wants.
So it doesn't affect anything.
Well, this is pretty unstable. Nitrate really is going to react with almost anything that comes in contact with it, unless it's aqueous, and then like the water stabilizes it, because like the water molecules would surround it and balance it out. But yeah, don't this whole thing of this. Where was I? This little note down here. Okay, this is true for any like organic molecule, meaning carbon, hydrogen, and oxygen. So if it's something else like this, then kind of all bets are off. But
the O is overall negative for 2 of them, and then positive for 1. How is the charge overall -1?
we have -1 formal charge here,
Oh.
-1 formal charge here, +1 formal charge here. This one's 0 because it's actually like how it wants to exist.
Okay.
So then the overall is -1. What else do we got? Polar bonds in a polar molecule. That's kind of fun. Yeah, well, yeah, but
One's like within it, one's like over.
correct. So let me give you an example. Okay, I have carbon tetrafluoride. This is the Lewis diagram of carbon tetrafluoride. Okay? This bond right here, polar or non-polar? How would I determine that?
You look at the
Electronegativity. Which of these two is more electronegative?
uh,
Fluorine,
yes.
by a lot. So this bond, polar or non-polar? Polar. This would have a partial negative charge, that would have a partial positive charge, right? So the bond is polar. But the molecule is nonpolar. Why is the molecule nonpolar? It's symmetrical. There's a symmetry to the shape of the structure. Right? So these outer atoms would all have partial negative charges in theory, but as a result of the geometry, they would all cancel out. Now, please be careful. What I have drawn is 2-dimensional, right? This isn't a flat square. This has depth. This is a tetrahedral shape. This is like one atom straight up and a little tripod underneath. Okay? That is the shape of a tetrahedral molecule. Now, it is perfectly symmetrical. I think I showed that to you and proved that to you when we were doing that stuff and flipping the shape around, right? Doesn't matter which one of those atoms I have facing upward, that shape is perfectly symmetrical. So long story short, I have polar bonds, but I don't have a polar molecule. These would cancel out because of the shape. There you go. This is just different Lewis diagrams. This one's going to have no lone pairs on the center. This one's going to have 2 lone pairs on the center. This one's going to have 1 lone pair on the center. Okay, if you draw all Lewis diagrams, you would kind of hopefully realize that. The formulas look the same, but again, Lewis diagrams are going to get us to different places. Oh no, I deleted my molecule. Shoot. Yeah, it is kind of funky. Let me go find it.
Yeah, this like definitely. Like a stem. Yeah.
Oh wow, how's aggressive? Could not add the attachment. Take 3. Now what? It's still yelling at me? Oh, there it goes. Now we're good. Oh no, don't do that. All right, it's back. Ready? Boom. Okay, so this one is a weird organic molecule. Now, they're probably not going to give you the stick version of it, but at every single intersection and end of a line segment is a carbon. Okay? So this would be a carbon. This would be a carbon. Carbon, 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 so on and so forth. Okay? This is a style of drawing organic molecules, where every end of a line segment and every intersection between line segments is a carbon atom. Now, there's no hydrogens drawn on here whatsoever. Carbon needs how many bonds? 4. So I would fill in hydrogens until I get to 4 on each carbon. 4 bonds, that is, right? So for example, this carbon right here, how many bonds does it have? How many hydrogens does it need? None. It's happy. It's got its 4 bonds. How many hydrogens would I need here? 2. Yeah, okay. Oxygen needs how many bonds? How many lone pairs? Okay. So hybridization, let's talk really quickly about that. Hybridization is identified based off of coordination. Okay. If I know how many things are being separated around an atom, I can identify the hybridization. For a review on hybridization, what it basically is orbitals are blending together. Now, the why of it occurring, don't worry about. Okay, it's too late in the game for that. Plus, they're not going to ask you that anyway. All they want you to do is identify it. That's all they want you to do. Can you pick out which type of hybridization this molecule has or that atom has? And the way you identify it is based off of coordination. Okay. How do I identify coordination number? What am I counting? How many things I'm separating around that atom? So for example, let's look at this carbon, I guess. That's a good one. How many things are being separated around that carbon? 3. 3 atoms. How many things are being separated around this oxygen? 4. Lone pairs count. You're basically looking at atoms and lone pairs around a different centralized atom. Okay? So what is the hybridization around something with a coordination number of 3? It's sp2. Okay? When the coordination number is 4, that equals sp3. When the coordination number is 3, that equals sp2. When the coordination number is 2, that equals sp. That's all you need to be able to do with hybridization. That's it. So in this molecule, when I'm asking you like, okay, what's the hybridization of the double bonded oxygen? Okay, let's look at that. What's the coordination number? 1, 2, 3. What hybridization would it have? It'd be sp2. The hybridization of the oxygen in the chain, right here, 1, 2, 3, 4. What's the hybridization? That's what you need to be able to do. It's literally just memorizing that relationship, and then you're good.
So do you have to the H's that you're not drawing?
Yes, you do. Totally. Yes. Yes. If I want to answer the rest of this, I absolutely need to do that. Now, sigma and pi bonds, they're not going to go there. I really don't think, but it's sigma is the first bond between any two atoms. The second and third are always pi. For example, here's a triple bond. The first bond is sigma. The next two are pi. So if I were counting which was which, this would be 1 sigma bond and 2 pi bonds for a total of 3 to make that triple bond. Counting various types of bonds, yes. Huh? Correct. 1, 2, 3, 4, yes. And every other bond between every other pair of atoms would be sigma.
I got that one in the test.
Pretty sure I said those exact same words in the fall, but you know.
Yeah, but we didn't listen.
All right, I don't have the pictures on mine.
This is where yeah.
The first bond is sigma. Any additional double or triple would be pi.
So it would just be all of the sigma, and then you count lone pairs.
Lone pairs aren't bonds. Nope.
They're not bonded.
I know the one that.
You're going to have to look at your sheet because I don't have all of these copied and pasted into my presentation. Let's review the names of various molecules. And let's review their angles. A. I think A is just linear if I'm not mistaken, right? What is it? I need a packet. Yeah, it's linear. Yeah. You know what? Hold on, let me do this. I'm thinking.
Oh.
Wait, why is there 12?
Because just like a PDF.
Yes.
Oh.
Can we just not tell Luca he's taking the final?
He is taking a final.
Yeah, he doesn't think he is.
Yeah, some things it's not taking.
Is that gonna be part of it?
I'll post it and then just leave it.
Okay.
Here you go.
Yeah.
This is from Unit 2. This is exactly what I wrote out to you in the fall. Beryllium fluoride. Now, if you notice, that chart that I have on the back of this sheet is organized based off of coordination number. Row 1, coordination number is 2. Row 2, coordination number is 3. Row 3, coordination number is 4, so on and so forth, right? That's the very first column listed on that sheet. Right?
Yeah.
Wait, so does that mean that the first one's SP? And then the second
Correct.
one is
Yep. What would what's the hybridization of this? SP. Let me go to the next one. Okay. This is a coordination number of 3. When you have 3 things separated in 3-dimensional space, you get a trigonal planar molecule, meaning a flat triangle. The angles between these 3 would be 120 degrees. What's the hybridization? sp2. If I have 2 bonds and a lone pair, coordination number is still 3. However, when I describe the shape of the molecule, I only describe the atoms, right? To describe the geometry, we ignore the lone pairs. So this would be bent. The angle would be 120. And the hybridization would be sp2, because the coordination number is 3.
I thought you said that, lone pairs don't count.
They count towards the coordination number,
Oh, but not towards.
not towards the geometry. In other words, like I don't describe the shape of my molecule based off of lone pairs.
Okay.
Carbon tetrabromide, this is coordination number of 4. sp3 hybridized. Tetrahedral and 109.5. Now, here's my guess. I sincerely doubt they'll give you anything with the coordination number of 5 or 6. If you've gone through any practice materials or a lot of practice materials, and I know some of you have, I cannot remember coming across an instance where they go beyond a coordination number of 4 and ask you a question about it. No, hybridization post coordination number of 4 is a dead science. It used to be taught, but then like a whole bunch of scholarly papers came out that basically disagreed with it. So they've dropped hybridization of larger molecules above coordination number 4. And in reality, I would not be surprised if the hybridization of like SP, SP2, SP3, I wouldn't be surprised if in 5 years I'm not teaching that either. Well, people are doing research on it and making sure that it's actually true. So that's not dumb.
Wait, so the first person was just like going out on a limb and.
I mean, it was originally a theory that was backed up by various things, and then now they're, you know, looking more into it. Yeah. Okay, so Vesper theory, valence shell electron pair repulsion theory. No. Do not. This is not.
I don't know, bro. Any more?
Let me make one more comment about shapes, and then you can go. You absolutely should know coordination number of 4 is tetrahedral. And you should absolutely know that the angle of that shape is 109.5. Now, even if my coordination number is 4, right? 3 bonds and a lone pair, coordination number is still 4. You can still write 109.5. If I have a coordination number of 4 with 2 bonds and 2 lone pairs, you can write an angle of 109.5. Long story short, coordination number of 4 makes a tetrahedral arrangement, and the angle is 109.5. That will show up somewhere, somehow on that test, I promise you.
So what's the F shape then?
Coordination number 5? What'd I say?
For coordination number 4, that they were going to be.
We separate the things in a tetrahedral shape, but if one of those things is a lone pair, I don't acknowledge it when I describe it, right? So in this instance, like they're separated the exact same way that these 4 atoms were. It's the same exact separation. It's just that I don't use that lone pair to describe the shape of the molecule. So I would call this a trigonal pyramid. Basically, it's the same shape. I've just removed the top atom and replaced it with a lone pair. So I describe just the atoms when I describe the shape. Oh yeah, trigonal bipyramid.
Yeah.
It gets all sorts of weird. Sorry, Gavin, I got nothing. You guys can go, by the way, home people. Thank you for your attention.
These people didn't want to.